record on this computer. So can anyone see that it should be being recorded now? I think there's like a red dot or something that appears at the top. Can someone confirm that they can see that?
No.
It's recording.
Okay, so we had no one yes.
Oh yeah, I see that it's recording.
Okay, terrific. Thanks a lot. Okay, so let's get started. Thank you very much for coming to this virtual webinar. And the idea is to do something that we haven't really done before at this time of year, but for people who have been to AGU, they may be familiar that we have run a pizza lunch each year at AGU in San Francisco. Hold on, let me, can the person who's making a noise unmute themselves? Mute themselves, thanks. So, and at the pizza lunch in San Francisco, it's a fairly informal affair where we go over the updates to GeoMapApp and then we just turn it over to the audience and they ask questions and we try and answer it. So this is going to be somewhat like that, where I'll give a very brief introduction to GeoMapApp, maybe 1 minute or 2 minutes, then jump into some teaching examples. But the main purpose of this webinar is to get you all to speak to each other, to ask me questions. Maybe you've tried using GeoMapApp, but you're not quite familiar with some of the functionality, so we can go over that. And then we'll take it from there. And if you do have questions, you can use the chat box to send a message to the group, or you can just unmute yourself and jump in with a question. Okay, so I think that's all of my slides. So let me get rid of that. And here is GeoMapApp. So let's go start it, and off we go. So I'm going to start off with a couple of plate tectonic examples, and you can just jump in with pointers, and I don't pretend to be an expert, so if I say something wrong, please correct me. So let's just say you're interested in an intro class, basic plate tectonics type stuff. Maybe you want to show, have one half of the class looking at where volcanoes are, another half looking at where earthquakes occur, and then start to delineate the plate boundaries from that. So I'm just going to run through how you could go about that. So in GeoMapApp, hopefully you can read the tabs across the top. There's still a couple of people. Let's see if I can mute them. There we go, I got it. So if we click on, let me just explain the layout of the window here. So we have some of the tabs where we'll find data under the data layers menu. File is where we have the import functions and the save functions. Portals are data sets that have specific enhanced functionality, and we'll look at one, maybe two of those later. And then under education, this is an education webinar, focused webinar, so I'll show you a couple of things under here. There are a number of GeoMapApp activities already existing, and you might be familiar with Margins and Geoprisms program at NSF, the decadal programs, and they have a bunch of mini lessons, and a number of those use GeoMapApp. So if we click on that, it should bring up the CERC site. The mini lessons are hosted at CERC in Carleton College. And you can go and search on the topic of your choice, like subduction factory, and there's a bunch of mini lessons here, and a number of those use GeoMapApp. So let's just minimize that. Also under there were some that I made with a master teacher a few years ago, and like there's one on seafloor spreading, there's one on erosion, that kind of thing, polar sea ice. Okay, so in the toolbar, there's our panning symbol, zoom buttons, our profiling tool that we'll use in a little bit, and then the grid loading that we may use as well. But I just want to quickly explain the structure of the base map that you see here. So one way I'm going to do that is to turn on this button, which is like a Phantom of the Opera mask. And that is a masking function that shows where we have the high resolution elevation data compared to where we do not have it. So on this map, oh, I should also say that, wouldn't you know it, but today we're doing some work on our Amazon service that services the tiles that drive GeoMapApp. So some things may take a little bit longer to come in than they would normally. So everywhere that is transparent has higher resolution data. On the land, we use the ASTER 30-meter data set. In the US, we use the 10-meter USGS National Elevation data set. And in the oceans, we have a combination. So if I zoom in on, say, this area down here, then you can see track lines. And what we're looking at here, these are the multi-beam swaths that come from research cruises. And we see the thin ones that come from the older multi-beam systems and the thicker ones that are from the more recent ones. And the gray stuff in the background is where we interpolate across the JEBCO 2014 data set to give us information where we do not yet have the higher resolution multi-beam data. So if you toggle the mask on and off, you can see that in areas where we have multi-beam, we have the higher res, and areas where we do not, we have the fuzzy background data. Okay, so I'll just go back to the global map. All right, so I'm just going to jump in with, let's say we'll look at earthquakes and volcanoes. So what I did, I clicked on data layers, and then I clicked on the orange thing at the top that brings up this separate menu. It just makes it easier to navigate the menus by tearing off the menu. And we'll go under geology, volcanoes, and let me just make this window a bit wider. Oh, wrong one, this one. Then you'll see that we have the Smithsonian Global Volcanism program catalog in here. So we'll just click on that, and here are the volcanoes. So we just have gray dots on a map, but these are all interactive. So if we click on any of these dots, then it lights up the table beneath, and this is the Smithsonian table, and we'll see that there's a URL here, and we can click that, and it should bring up the Smithsonian page for that particular volcano, like that. So that might be useful. Then if we wanted to change the symbols, that's very easy to do. Now we know that volcanoes are typically triangular in outline, and that lava is orange in color. So what we could do, we can color the symbols. So let's color like this, and we'll choose an orange color like that, and we'll choose triangles, and we'll do big volcanoes, and there we go. So now we have proper triangle shapes for the volcanoes. And you can zoom in and see like to the Pacific Northwest up here. And if we click on these, then this is Mount St. Helens here, and it tells us in the table. And here we have that one, and that is Mount Hood. And again, if you click on the hyperlink, it'll bring up the information from the Smithsonian page about that. So you could have, half of your class, say, look at where the volcanoes are, and you can start to see the plate boundaries, of course, right away. But you could also bring in the earthquakes, and for that, I'm just going to get rid of the volcanoes and switch to earthquakes. And over here, we go into geophysics, earthquakes, and we go into the USGS catalog. And I update this typically twice a year. So let's just bring in the earthquakes greater than magnitude 6.0. And so you can see if you're running an intro class, you might be able to get some insight from your students on the locations of these two things. Now, the earthquake table also links to data at the USGS site. So one thing we can do, we can click on a column header and it will sort that column. So here we have the big one, the Biobio earthquake in 1960. Then up there we have the Alaska one in 64 and the Banda Aceh earthquake. So if we just click on the link there, then we get slowly, it's bringing in the USGS information, and it should not be undefined. It worked fine this morning. There we go. And that's the USGS page with all of the details about that earthquake. Okay. So I'm just going to keep going for a couple more examples that are going to get more and more involved as we go along. But like I said before, just jump in with, oh, hold on, there's a chat. Can the symbol be changed depending on the type of volcano? No, so that's a good question, Erin. It's all or nothing with the symbols. Either they're all circles, or you see the range, circles, squares, triangles, or stars. So you change the whole lot in one go. Good question.
Can you change it by maybe the size or something using scale? Because you can change the size of the earthquake dots,
right?
Their size.
Yeah. So what happens is with the color and scale buttons here, any numerical column in the table can be operated on with these functions. So like for earthquakes that we have here, I can color them according, say, to depth. And so there we go. We'll drag these lines and change the color scale. And if we zoom in, say, on the Tunga Kermadec area, so here we have the earthquakes that are now color-coded according to depth, and I can change their size dynamically according to magnitude. So we choose magnitude, and we have it like that. So the configure window allows you to change everything uniformly, all the color, all the symbols, all the size. And these color and scale ones allow you to change them dynamically. So if there was a numerical column in your table that you wanted to scale or color on, then you could certainly do that. Okay, so I'm gonna close that, go back to the world, and load in the crystal age of the ocean floor. So let's see. So I have to go and find it. It's under lithospheric plates. Oh, I should say, if you cannot find data sets, we have about 4,000 or 4,500 data sets built into GeoMapApp. So if you can't remember where things are, if you just type in the top bar here, crustal, then we'll get all kinds of stuff popping up. Let's see. It should, we want to go under crystal age, there it is. So this is Dietmar Müller's crystal age grid from 2008, and it loaded it. And this has slightly different functionality than what we've just looked at, because here we're dealing with a grid. So if you notice, let me just make that, actually budge this window over. As I move the mouse around in the window, if you look just above up here, you'll see the numbers change, and the number just above the mouse there is the third dimension of this grid, which in this case is crystal age. So there it's 120 million years. And as you move around, you see 7.6, and it gets older away from the ridge. So let me just do a couple of things. I'll turn off the shading so it looks a bit prettier, and we can change the color scale a little bit to make it look like that. And then if we zoom in, say, actually, let me also draw contours. So if we put contours on here, so I just click the contour button, and let's say, we'll look at what 50, oh, that's not very good. Let's do more contours. So we can do, say, every 10 million years, and we'll bold them every 50 and see, okay. So now we have contours on, and let's go and zoom to the South Atlantic, like so. And now let's draw a profile across here, and we can start to look at things like spreading rates. So I activate the profile button by clicking there, and I'm just going to try and follow the great circle route there. And here we have the crystal age against distance across the South Atlantic. And like I mentioned before, if you put the mouse in the middle in the dark blue, you'll see it's very young now, and as you go away to the continents, it gets older. Well, one thing you can do that's very helpful for students is you can reset where the zero distance is on this scale. If you just click at the base of the V shape there, then it re-zeros it, and it makes it easier to do calculations. So here, you'll see that it's 0 age now at 0 kilometers, and that the distance goes off in both directions. And if you wanted to have students calculate the seafloor spreading rate, then you'd have them look at speed equals distance over time. Well, distance here is on the horizontal axis, and age, the time, is on the vertical axis. So the spreading rate is actually the inversion of the gradient. It's 1 over the gradient. So that might confuse some students. Okay. So any questions on this? If not, I'm going to show a similar profile, but this time between Australia and Antarctica. So if we just go to the panning symbol and move over, and say go over here, so we have Australia and Antarctica, and draw a similar profile, say we do it down here. Aha, now we get something quite different, where we have two different gradients here on the profile. And here we have this is the shallower gradient, so it's the faster spreading. And out here, the older ones are the slower spreading. And you can see that in the contours as well. If you're attuned to looking at contours, you see that the contours are squashed together. So the plate wasn't moving very far over a long period of time, and then it sped up quite a bit. So you could have your class, one set of students looking at spreading rates in say the South Atlantic, another in this area, another in the Pacific, and they can compare and contrast and that kind of thing. Okay, so hopefully people might be able to use that in a class, say. Does anyone look at magnetic anomalies? I think some of you may. So I'm going to, oh, somebody raised a hand. Now I have to work out what to do with a raised hand. Hold on. The person who raised the hand, oh, okay, right, there we go. So Lisa says yes to magnetic anomalies. So let me just get rid of the things in here. Oh, I should also say that the layer manager has a transparency function that allows you to change the transparency of the layer on the top. Notice that with the transparency, if you drew contours, the contours remain. And that came from a request we had from William Wilcock back in maybe 2016 at one of our AGU sessions. And he said he would love to show the contours to the top of the subducting slab, just the contours without the underlying grid. So we added that function. Okay, so I'm just going to close that, and we'll get rid of that and go back to the world. And excuse me, going to load the magnetic anomaly grid. So just let me get rid of that, and I'll go back into the data layers, make it a bit wider, and go into geophysics, magnetics, and you see a couple of options that we put in. There's the EMAG2 data from 2013. So it's loading the grid, and it looks a bit messy like that. But what we'll do is, let's find out where we are. So, okay, so if we zoom up to the Cascadia region in here, then you may recognize this from the Raffin Mason paper from 1961. And I'm going to change the colors so it's not these and change the color palette so it's not these rainbow colors, but it'll be black and white. Let's just choose that, turn off the sun illumination, so now it's looking more like the zebra stripes. And we can do a similar thing if we wanted to look for, say, the symmetry of the anomalies. So if we click on the profiling tool, then I think maybe let's take a profile across here. And here we go. And as you move the mouse around in the profile window, you see the red dot shows you where you are. And when you look at this, you can maybe see a hint of symmetry. So let me just say re-zero the distance scale there. So you can see that we have the central anomaly from the ridge axis, and going out, I actually chose that fairly well, I'm surprised. About 50 kilometers away from the axis, we have this symmetrical anomaly. And then going out to about 80 kilometers, we have this one, and so on like that. So if you have a class where you have looking at magnetics, then maybe this is something that you could have your students do to look for the symmetry of the anomalies at the spreading ridge. Okay. So I mentioned the subducting slab, so we're in the Cascadia region, so we can bring that in as well. So let's just get rid of that window. And I'm actually going to turn off the magnetic anomaly grid and just budge over this way a bit. And I'll get rid of the overlay up here as well. Okay. So here we have the Pacific Northwest and the Juan de Fuca plate and the spreading axis there. And we see the line of volcanoes. So if we go and look at, let's see, we want to go under lithospheric plates, and we have the subduction slab depth. Then under here we have the Cascadia and the McCrory grid that show et al. That shows us the depth to the top of the subducting slab. So brought it in, and as I move the mouse, you see that it's shallow here and it gets deeper as you go away from the trench, obviously. Well, obvious to us. But if we draw contours on there, then we'll do 10-kilometer contours, and let's bold them every 20 kilometers. And we have this effect here. Yeah, does someone have a question? No? Okay. So if we draw a profile across here, then we see the profile of the subducting slab, the top of the slab here. So you might right away realize that, oh, if there are grids like this for other trenches, for other subducting slabs, maybe you can compare the geometries of these subducting slabs. Okay, so let me see. Okay, so we do have grids that are from the other subduction zones, and I can show some of those. Actually, before I do that, I think some of you may cover tomography with your students, and let me just see, is there a way to have a continent somewhat transparent as the overlay? So Chelsea asked a question about the transparency. You can change the transparency of the layer on top. You could switch the order. So now I just flip the order of the layers in the layer manager. So now the continental, the base map is on top. And if you change the transparency of that, then yes, you can do it that way too. So hopefully that answers your question. Okay, terrific. All right. So if we wanted to also, say, bring in a tomographic layer, then let me minimize that. If we go into the geophysics again, we have some tomographic models that we put in. So we have North America. And here we see the Gao and Shen model of the Cascadia region from 2014. And let's say we look at the 94-kilometer depth layer. Then here it is. So this is the shear wave VS, shear wave velocities at 94 kilometers depth. Right, let me just back up because someone just pointed out, Erin just pointed out that if you play with the transparency, you can see that the volcanoes in Cascadia line up with approximately the 100-kilometer slab depth. Very nice, thanks for pointing that out. So here we have the tomographic layer, and I know that seismologists love the jet to invert palette. So to change the palette, I clicked on the palettes menu in the grids manipulation tool, and we can click on that, and there it is. If you look in any tomographic paper, they seem to use this palette, so we built it in. So here we have the tomographic layer, shear wave velocity, and we can bring up the grid for the subducting slab and make that transparent. And let's see, 20, 40, 60. So around here, this is around the 90-kilometer line here. So the tomographic layer corresponds to about that depth in the down through the Earth. Okay, so if we were to look at subducting slabs at different trenches, then let me just turn off that tomographic model, and I'll actually turn that off and go back to the world. And if we go to subducting slab, you'll see that we have different data sets built in. We have the Ellen Syracuse and Jeff Abers model from 2006, and we also have the USGS Slab 1.0 model. So you can choose your favorite subduction zone. So let's say choose South America, and it will load the grid for there. And we can do the same sort of exercise by looking at the geometry. We click on the profiling tool, and we get a geometry that looks like that. So you could have students go around the world and look at the geometries, distance from the trench axis to volcanoes and that sort of thing. Okay, Leslie asked the question, can contours be labeled? And short answer, no. Sorry. It's actually really complicated to label the contours, so we don't have that functionality yet. So I guess if you wanted to label, then you would need to, oh, look at that. Maybe I did that too much. You need to bring the map into Illustrator or a tool like that to draw the label, to annotate the labels. Okay, so let's see. I'm going to show one more thing, I think, and then we'll turn it over to questions and answers. Keeping on the theme of plate tectonics and plate motions, let me just get rid of all of these. I forgot to say that if you click on the tourist information symbol in the layer manager, it should bring up something useful about the data set. It typically points to the source. The USGS occasionally changes its URL, so the one we were pointing to before maybe got subsumed by something else. But if you click on that, it should take you to the source of data. Okay, so let me get rid of this and get rid of that. And let's look at, someone asked, so Jessica, hi Jessica, can you show the profiles side by side? No. You can certainly, when you draw a profile, so let me just bring this one back in. And so we do the profile again, like that. Then if you look up here, there's a save, and you can save it as a JPEG image or even as a table. So you can save the different profiles and then stick them side by side. And you can also change the scaling on the axes to get them to match. So I guess that would be the way to do that. Slab 2.0 is out, great. If, yeah, so I will go and look for it and hopefully we can build it in. Jessica, if you have a URL that points, Ross, if you have a URL that points to Slab 2.0, if you could just email it to me, then I can see if I can put those grids into GeoMapApp. Okay, so let's see. We were going to look at, oh, this is a really fun one. So I'm going to go back to the world and get out of the subducting slabs and instead look at some plate deformation data. So for North America, we have quite a few different data sets that are put in GeoMapApp. One of them is Eric Calais' grid of the vertical velocity from a few years ago now. But here's the grid that loads. And I'm going to draw contours on it just so we can see the hinge lines. So let's see, let's just go either side of 0. So I'll go from -1, 0, 1. And here are the contours. And if I zoom in this area, then turn off the shading, then you'll see that if I move the mouse around up here, you'll see that the vertical velocity is around 8 millimeters a year going up. And if I come on the other side of the hinge line, then the blues reflect the negative, the component that are going down. So this is the, after the ice sheet retreated, then the area that was under the ice is rebounding upwards, and the peripheral bulge area is going in the opposite direction. So we also have the MIDAS data from a few years ago, and that's really fun to look at. So if we bring that in, it's in the same menu, MIDAS North America. This is from University of Nevada, Reno. And this is a tabular data set. And let me just go this way a bit, okay. Then we can color this one. So I'm going to color these symbols and going to look for the up velocity. Here's the up velocity. And let me choose a different palette, just one that's a bit brighter. So we'll say do Jet 2, and then we'll drag these lines around to change the colors, like so. And for these, about -5 to +5 gives us a nice range of colors. Okay, so here you can see that the individual stations, they're linked here. These are the MIDAS stations. Oh, and if I go grab, here's the up velocity column. Well, let's bring it over to the left. You can just slide these columns around to make it easier if you have a big table. Okay, so here we have the station name, the link to the station, the latitude, longitude, and now the up velocity. And so here we see that the ones up here are going up with the positive values, and the negatives down here. So if you're teaching a class on glacial isostatic rebound, that sort of thing, then this might be a useful data set for that. Okay, there's a question about Fulcrum mechanism solutions, and I'll show that in one sec, but I do want to show the save session function, and that might be super useful if you're teaching. So here we have a grid in the background with some contours on it. We have the dots that have been colored in a particular fashion. If we go to File, Session Manager, Save Session, then it's going to, it's saying, where do you want to save it? I hit Save, and where do I see it? Okay, so here's the one. That's one I did earlier. Get rid of that one. Yes. So here's the file that I just saved. So what I'm going to do is I'm going to minimize this instance of GeoMapApp, and I'm going to start another one. So the other one is still running, but we're not going to refer to that for now. So I'm starting a second one at the same time. And for those people who joined a little bit later, I was explaining that we're having some work done at Amazon with our base map tiles. So it's taking a bit longer for the base map tiles to come in than normal. So sorry about the delay. Okay, here we go. So here's our new GeoMapApp window. So you can pretend that you are now the student and your professor has created this session file. And if we go to File, Session Manager, import the session, then I go find it. It's the only one I have. And I hit Open. And GeoMapApp goes off by itself and automatically brings everything in to just how we had it. So if we bring up the other window, which is down here, so this is the one that we saved, and here's the one that we just imported. So if you have a class of students, rather than having to spend ages explaining to everybody how you click on the menus, go here, load this, do that. The professor can just save the session and then share that one little file. You'll see that this file is only 3 kilobytes in size. So that might be really useful for cutting down on time, dealing with where the data layers are, and actually having more time to analyze the data. And it works on pretty much most of the data sets. The one set of data sets it does not work on is imported data, because we have no control over how things are stored on your own computer. So if you have imported your own data sets, like a spreadsheet or a grid or a shapefile, then you will not be able to do the save session, or it will not capture that particular layer in the save session. Okay, so this was the one that we imported pretending we were a student. So we can get rid of that one and we'll work with this. So they now have access to the full data set, just like as if they had done the whole thing from scratch. So if you were to look down in the Houston Galveston area, then, and we bring up the layer manager and make the grid somewhat, oh, we're still bringing in the base map tiles, the Gulf of Mexico is in here. These negative values are the ones around Houston and Galveston, where the hydrocarbon extraction is taking place, so the ground is going down. And if we were to, let me just zoom out a little bit and budge over to California, then, oh, and you can make this window taller so we can see this a bit better. If we zoom in on this area in the Central Valley, then you'll see there's some negative values here. Make the window a bit too, and we need to go find that up velocity. Here it is. Here's the up velocity column, and I've just sorted it and gone the other way. And so you'll see that the first negative value is up there, next one is there. But if we capture all of the negative values down to, wait, it's going the wrong way. Sorry about that. Okay, here we go. So I was at the bottom of the table instead of the top. So let's say we're gonna capture all the negative velocities down to 10 millimeters like that. Then we should see, did I click on the right thing? Then they are in the Central Valley here, where the, you can see them being lit up here, where the groundwater extraction is taking place, and so on. So that might be useful if you're talking about impact of humans on our planet, looking at groundwater extraction. Okay, so someone asked a question about focal mechanisms, so let me just jump to that, but I want to be mindful to give us time to answer your questions. So let me get rid of that. And actually, I'm just going to kill this entire window and start again. And whilst I'm bringing this up, does anyone have interest in looking at a couple of ice sheet related data sets in Antarctica? So any takers for ice sheet, thickness, that kind of thing? If yes, then, okay, so I see a couple of yeses coming in, so we'll jump to that in a second. Oh, I see lots of yeses coming in, all right, okay. So, oh, come on, Amazon, you can go faster than this. So this should all be resolved and be back to normal speed fairly soon. Okay, so the question was about earthquake focal mechanisms. So if you go into portals, and you'll see that we have the CMT solutions here, and here they are as blue dots. So this is the data set that we get from the global CMT project, which is also hosted at Lamont. And I update this also about twice a year, but there's always a few months delay in getting the final solutions. So when I last updated it earlier in the summer, it was up to January of this year. So at present, this doesn't look very interesting, but if we zoom in, say, I don't know, let's go in to, say, an area up here on the Mid-Atlantic Ridge, then when we get beyond a certain zoom level, suddenly we see the beach balls, the focal mechanism solutions appear. And we can see the faulting along the ridge axis. Again, the base map should be coming in. Come on, base map, you can do it. And along the transform faults, we have the sideways motion there. So, but there we go. You get the idea that this is along the ridge axis, and here we have the fracture zone solutions. If you click on any of these symbols, then down at the bottom, you see the solution for that particular event. So that might be useful for your teaching. And get more info, I think that brings up, yeah, this brings up the global CMT page. Okay, so I'm going to close that, and oh, because we brought in a layer, we brought in an imported session, this extra menu item appears, My Layer Sessions. If you don't want it, you can just get rid of it there, like that. So if you're already in GeoMapApp, you can flip between projections using the projection button. So I'll just click on South Polar. And this was taking a while before because it's now trying to load the South Polar base map tiles, which is being delayed at Amazon for some reason. But it will come in. Every time I give up and start a new session, the other one immediately comes up. So let's just wait for it to come in a sec. And there we go. So when Amazon gets fixed, then this should take just a second or two. So here we have the South Polar view, and we can look at a couple of the built-in data sets. So if we go to data layers again, and let me move this over here, you'll see we have a whole cryosphere menu, and let me just make that a bit bigger. So one fun thing to look at with students might be some of the ice sheet dynamics, and we have a couple of data sets for that. So under ice sheet, we have the bed map data set, so bed map v2. So one thing you can bring in is, say, the bed map bed elevation. So this is the rock bed underneath the ice sheet. And then if we bring in, say, the surface elevation, the surface of the ice sheet on top of that, then we click OK, and it will bring that grid in as well. So now I've got the two data sets. Well, right away, you're probably thinking, oh, if you draw a profile between the two, and for that, I'm going to zoom in, say, to this area here, maybe going a bit more. And you need to be away from the floating ice sheets for this. But if you are over land and you say, draw a profile up here, then here we have the elevation of the bed underneath the ice sheet and the elevation of the surface at the top of the ice sheet. And let's say we look at, let's say we look over here. So here we're around 400 meters. So the bed of the ice sheet is about 400 meters high up in the air, above sea level. And at this similar location, we see that the top of the ice sheet is around, what, 350, give or take. So the thickness of the ice between the two is around, what, 2,800 meters, something like that. Well, we actually have the ice thickness grid, so we can check our calculations, and it'll bring that in, and we draw a similar profile, something like that, and we can see that here, say we're around 350, 400 meters, around just under 3,400, so we should be around 3,000 meters in ice thickness. So hey, it works. How about that? So another data set we have that's really fun to look at, oh, the top of that window got chopped off, so sorry about that, is we have Eric Rignow's ice velocity data set. So if we just minimize that and go, we have the version 2 data set, and this is just fabulous to look at. So let me bring the top up, and let's just change the palette to this to make it look a bit more attractive. So let's do the Jet 2 again, turn off the sun illumination. So now we can see the velocity of the ice sheet in those locations. And like before, wherever you move the mouse, if you look in the top bar, you see the number. So here it says 2.3 meters per year. And as we get towards the ice streams, then we suddenly zoom up to 686 meters a year and so on. And if you wanted to draw a profile across here, so we activate the profiling tool again, we'll do a similar profile to the one we had. And so now we have the same data sets that we had before, and now we have the ice velocity as well. And if we were to look down in this area, and this is just spectacular, then we can see, it's almost like artwork to me. Then you see the really fast speeds in here. We're what, 1,000 meters a year. And if you were to draw a profile, then you'll see how the velocity goes way up as you get close to the edge of the shelf. Okay, so hopefully some of the things I show, the functionality, the different data sets, might be of interest to people. I could keep going for hours and hours more. There's so much built into GeoMapApp. Like, we didn't even look at the velocity vector portal for the GPS stations. Someone asked, how long did it take to develop this app? I think we're now in 15 or 16 years of development, and we are funded through NSF for this. So I want to turn it over to you, and please ask questions. If you have any questions on functionality or different data sets that you might be able to use in teaching, then ask away. Or if you want to share teaching ideas with someone else. Everyone's gone quiet. Does anyone want to see the GPS velocity vector portal?
Andrew, that's why we're all quiet. We're all playing with the data.
Oh, okay, that's good. This has been a bit of a whirlwind, but whilst we're on Antarctica, if I'll wait for questions to come in, but whilst you're thinking of questions, we can look at some ice penetrating radar data if you would like. Anybody interested in that? Ice penetrating radar, Lake Vostok. Any takers? Yes, no? Okay, Joanne, thanks Joanne. Okay, more people. All right, so let me turn off some of these layers. I'll keep the ice thickness. All right, and I'm gonna get rid of that. And what we need to do is budge over towards Lake Vostok areas, over here somewhere. And we'll go into, I can't remember where this menu item is. So I'm just going to type Vostok in the bar and hit return. And various things come up. That's the one we want. I want to put the outline of Lake Vostok there. Okay. Oh, hold on. Let's... Okay, so Ross, I'll answer your question in a few minutes. Okay, so let me just show the ice penetrating radar, and then we'll get to a couple of the questions that came in. Thank you very much. So let's see. I'm delighted that you're asking questions. This is why we're doing this. So I want to go to portals, and under portals, you'll see that it says radar profiles of Antarctic ice thickness. So let me just get rid of this, and the window changed a bit. So let me just make the window a bit bigger. So here we have the available data sets. So we want Vostok, and if we zoom in a bit more, so you'll zoom into here. So you can see the lake outline from Michael Studinger is in the background. The colors in the background are the ice thickness, and these black lines are the profiles for the ice penetrating radar. So if we click on one of these lines, let's say we choose this one, then we can load that radar profile into the window below, and we can say zoom in a bit, And here you have the profile, and you see here's the lake surface here. And as you scroll around, oh, I should say that the red, so the line that was chosen is yellow. The red is the portion of the line that is shown in this window. So as we move, you can see that red line like a caterpillar crawling along. And then we get to the other end of the lake, and there we go, up the side there. So we can also load in a cross line and load it into view 2. And here we have it like that, and we can go in like so. We can even switch to inverse video if we prefer that view. And you can digitize these horizons. So if you click on the digitizer, then I'm not doing this very well, but there you go. You can digitize like that, and you can save the digitized points. You can import them later. So that might be something you want to do. Let's see, so that's the ice penetrating radar. Oh, I should say, I completely forgot to say that anything that you see in the window up here, you can save it as a map. So you just save the map and save it as a JPEG, and it'll ask you where you want to save it. Let me put it on the desktop and save it. And we should have, there's the picture right there. So then let's see. Okay, so let me, there was a question. Oh, whilst we're still here, we have the ice thickness loaded. So let's just show a profile, a similar co-located profile. So here's the ice thickness from the BedMap dataset along that line. So you see where we go over the lake bed, then we have the very thick ice that goes way up above 4,000 meters in thickness. Okay, so let's see. All right, so I'm going back to questions. So Ross asked a question: if GeoMapApp cannot be installed locally, can the web browser version, does it do the same thing? Yes, it does. It just does not require you to have to install Java and GeoMapApp locally. So what we call the web start version has the same functionality, so good question. I should also say that we're thinking about rewriting GeoMapApp using, we haven't decided what yet, or what language or tools, like we might use Esri modules, we might use open layers, but it's on the cards, and we would have to apply to NSF for a grant to do the rewrite, but it might allow us to avoid having users needing to install Java, because that is an issue for, especially for school teachers at middle schools and high schools that don't have control over the computers in the computer lab. Okay, so yes, so the question's about the velocity vectors. So let me just get rid of GeoMapApp and go back into it, and keep your questions coming. So, oh, I shouldn't have done that, because now, oh, it might go a bit faster. Okay, so Amazon seems to be behaving itself a bit better. So if we go into portals, this is one of those data sets that has enhanced functionality. So we find it under portals. And what we have is, what we did a couple of years ago is we worked with UNAVCO and got some of their SNAPS files, if you're familiar with the SNAPS solutions. And so we can load these in. So I'm choosing the EarthScope Plate Boundary Observatory PBO dataset, and hit the submit button. Oh, and we see this. So let's zoom in to North America. So these are the velocity vectors, and which did I choose? I chose them, the reference frame is IGS 08. Well, if we go in a little bit more, and so we see the whole continent is moving over that way, but we also have the North American reference frame, the NAMO8 ones. So if we choose those instead, then we see that now that we're holding fixed the North American plate, then pretty much everything is not moving anywhere, but we see that all the action on the West Coast. So if we go over to the West Coast, then we see that over here, the plate is moving very quickly up towards the northwest. So we can change some of the display functions here, similar to the velocity vector tool that UNAVCO used to have. They stopped developing theirs, oh, maybe 5 or 10 years ago. So we thought it might be useful to put it into GeoMapApp, the similar functionality. So we can choose to decimate some of the data. So say we only want to show 1 in 5 arrows like that. We can change the scale by changing the number there. We can put the error ellipses on it, like so, and you see the error ellipses there. So hopefully that might be of use to you. The station names are down here, all the data from the snaps files. Okay, so let's see, we're getting very close to 1 hour. So did I miss any questions? If you have a question, just shout out. Let's see. Oh, there's a question about climate data. Yes, we do have some climate data sets in here. So let me just close this and say go back to the world. If you go under data layers, then you'll see there's a climatology menu. We have a few data sets actually. I think under oceanography, there's like temperature, ocean temperature, and salinity, and these are data sets that, let's see, recent months. So these ones, sea surface temperature, this is being pulled in dynamically using what's called a web mapping service. So we go to, I guess we go to NASA for this and pull it in. So as it changes at NASA, then the new version gets pulled in right away. And you can see the temperatures here. Oh, and I forgot to bring, how do I get this down here? Here's the legend up here, the color legend up there. So we certainly have that. If you go into climatology, oh, right, we have some of these. Some of these are really nice to look at. And you can, so here's cloud cover. So right away you can talk about the arid tropics. Why are there deserts? The Sahara, Kalahari, Australia, that sort of thing, the Southwest. Let's see. What else is there? Global temperature. Let's see if that comes in. Ooh, okay. That has a different color bar. I'm not sure I like that one. Where is it pulling this one from? So this should link to, so it's linking to the NASA data set. Oh, okay, so it is, that is the data set today. There you go. So that's the where we pull the data set from. Land temperatures, right? Yeah, daytime, nighttime, they're often interesting to look at. Again, so there might be something wrong with the web mapping service there. Yeah, so there's lots of different climatology related data sets. What's the albedo one? Okay, so you see high albedo where you have the ice up there. Okay, so I think that we're at 1 hour. So does anyone, I say someone had a question, are we going to distribute this? Yes, I've been recording it, so I'll send, we'll actually put it on our YouTube channel. I completely forgot to say that, sorry. If you get stuck, go into help, there's a user guide that comes up right here. And this user guide, I updated it last year, but it has everything you can possibly think of about GeoMapApp. It goes into all kinds of detail, explains all the functionality, and there's also a cookbook section that I forgot to say. So if you look here, like how do I import, say, a shapefile? And it'll take you step by step through importing a shapefile and what you see and so on. Let's see, also under the help menu, you'll see the link to the tutorials, the videos we have on YouTube, and this is where I'll post this webinar as well. So you see them listed here, and if you go to the channel, then you can see all of the videos. I think clicking that should bring them all up. And there's all kinds of videos in there that we've done over the recent years. Yeah. So any other questions? No other questions? All right, well, I think because we're at 1 hour, that I'll wrap it up here. If you do have any questions on GeoMapApp, then feel free to email me. We answer every email. And we're probably going to do another webinar virtually for AGU, maybe the week after AGU, when people have calmed down after the craziness of AGU. And so if you have any questions between now and then, just email and we'll see what we can do. All right, so thank you everybody. Thanks for coming. And I hope that you have a good day, and I will send email once I post the recording. Thank you, bye-bye. If anyone does want to stay on and ask extra questions, then I'll stick around for a few more minutes, so feel free to do that. Okay, so I'm going
Andrew?
to, yeah.
Paul had asked, it kind of got lost in the thanks, about plate reconstructions. So you don't have any moving parts?
No, we do have plate outlines, so let me just get rid of some of these data sets. Come out to there, come out to there. Let's see, get rid of that. Plate outlines, I can't quite remember what this one is. Yeah, so we have the plates like that. So if you're doing the earthquakes and volcanoes or whatever, then you could have it like that. We also have Peter Bird's data set from his 2003 paper, and it's not the optimal way to display it as symbols, but it has all the values. So if you look here, you can see there's velocities, the azimuth of the velocity, the divergent component. So if we, let's see, if we put this like this and zoom in, say, on the North Atlantic and click on one of these dots, then we see the velocity, the divergence, so most of it is diverging, which is what we would expect for a spreading zone. Depth and other data from his paper. So we don't have like movies that show the plate reconstructions, but we do have.
Andrew, you have one category, yeah, for plate reconstruction. What is that?
So this is the depths of the oceans going back 140 million years from plate reconstruction models. So if you bring that in, then I don't know where these are located. So let me go back out to the world. I've not played with this one that much. So you can see that 140 million years ago, then this area was 5,000 meters deep, and it got shallower up here. So if you went back with your plate reconstructions, then this should mirror how that is all organized. And then you can go through the different years, different models, bringing them in and seeing how they changed. So like so. And then the data set for that, let's see if it tells us where it comes from. So it's coming from EarthBite, which is Dietmar Muller's team's site. So it's the Paleo age grid. Yeah, so if you read this, it'll explain exactly how they get these depths for the oceans going back 140 million years. Okay.
And back to climate, Andrew, do you have paleoclimate data, even if?
Oh, sorry, that's my my house phone ringing. Do we have paleoclimate data?
It was under climate.
Oh, there was? Okay. Oh, you know it better than I do. It's been a while since I looked under that menu.
I didn't see that.
Past climate. Okay, there we go. Right, so there are some data sets under here. Lake glacial temperature. Oh yeah, so there's the lake glacial maximum. Whoa, look at that. So this is a tabular data set, and if you click on one of these, it'll give you the position and the, what's it giving us? The percentage of vegetation, soil, and again, you'd have to look at the source of that. So it's coming from GeoMapApp, and I'll explain what the different components are in there. Atlantic sea surface temperatures, what's that one? Let me turn, so for a tabular data set, what I need to do is just get rid of some of these data sets. Get rid of that one and get rid of that one. And it should, I'm going to get rid of, oh, wrong one. Click the wrong thing. But if we load that one again, what's it showing us? So some depth age models, sea surface temperature. So again, you'd have to look at what there is in that. I would say that generally, most of the data sets in GeoMapApp are solid Earth related. I didn't show all the geology maps, didn't get to that today. We have a whole bunch built in. But you also see that we have some climate related things, some oceanography. So if you're aware of data sets that you think would be really useful to have in GeoMapApp, then please point me to them and I'll see if we can get them in. Sometimes we have formatting issues, but generally we can bring most different types of data sets in. All right, so any other last questions? All right, so.
Thank you so much, Andrew.
No, thank you for coming. I really appreciate that so many people signed up and actually joined the meeting. That's great.
Thanks a lot, Andrew.
No problem. Just email if you have questions. Okay, so bye everybody.
Bye.